Hello, I Anand Jain from Hanumangarh, Rajasthan welcomes you to your favorite Shridevi Classes YouTube channel where we inculcate interest and confidence in science and engineering subjects. Today in our playlist Basic Electrical Engineering and Class 12th Physics in our chapter Alternating Current Circuit we'll understand the behavior of pure capacitance in alternating current supplies, and will understand that when sinusoidal alternating voltage is applied across a capacitor, the current through the capacitor is again a sinusoidal current of the same frequency, but current leads voltage by a phase angle of 90 degree. And in this condition, capacitor stores energy when voltage increases and release the same amount of energy when voltage decreases, and average energy consumption in a cycle or long duration will become zero. And we say such current which is 90 degree leading to voltage in phase is reactive current, and power associated in this current flow from voltage source is reactive power. So let's understand pure capacitance in alternating current supply. Capacitor is a passive two-terminal element. Capacitor is made up of two metallic conductor plates which are separated by a insulating dielectric substance. Now this configuration can build and retain charge when voltage is applied across conductor plates which are separated by dielectric substance, and charge which is built and later on retained when voltage is withdrawn is directly proportional to the voltage applied across capacitor plate. Now this Q proportional to voltage proportional relation can be converted into equality using a constant known as capacitance, and our relation will become Q is equal to CV, where capacitance is property of this configuration to build and retain charge per unit of applied voltage, and capacitance is measured in farad, and practical capacitance got a small size and their capacitance are measured in microfarads only. In the charging process, when equal amount of opposite polarity charge on plate increases with increase of voltage across capacitor, the in-between dielectric insulating media also get polarized, and this polarized state of dielectric media store electrical energy. Now the same stored energy can be released during discharging process when the charge on plate or voltage across capacitor decreases. For a capacitor of capacitance C farad, when voltage across it is V, then its stored energy is half CV square joule. And in terms of charge on plate, for C capacitance capacitor, the stored energy is half Q square by C, and this stored energy is in the form of electric field in the polarized state of dielectric insulating media. In capacitor, actually the energy is stored by insulating dielectric media, and these conductor plate just become a via media to exchange that energy from external means. And during charging process, external source supply energy to dielectric substance, and during discharging process, this dielectric substance release its stored energy to external circuit. Consider a capacitance of C farad connected across a standard reference alternating voltage supply, and instantaneous magnitude of standard reference alternating voltage supply is given as Vm sin omega t, where Vm is maximum value of sinusoidal alternating voltage and omega is angular frequency of supply voltage. And we know on capacitor plates charge is directly proportional to voltage across plate, and proportionality constant is capacitance, and Q is equal to CV. So when applied voltage is Vm sin omega t, the charge on capacitor plate is given by mathematical trigonometric expression Vm C sin omega t, and charge voltage both are proportional and got similar type of sinusoidal time variation. So instantaneous value of charge on capacitor is directly proportional to voltage applied across it, and as voltage increases, charge on capacitor also increases and become maximum at that instant when supply voltage is at its peak value, and as voltage decreases, charge also decreases, and after every half cycle this charge alter its polarity or position Since the charging current is the rate at which charge enter or leaves capacitor in this circuit, and time rate of charge flow is charging current, and if in place of capacitor charge we write Vmc sin omega t and perform a differentiation, then Vm and C are constant, and differentiation of sin omega t is omega cos omega t, and this Vmc omega become expression for amplitude of current or peak magnitude of charging current, and charging current becomes a cosinusoidal function. We can write peak magnitude of current as, in place of Vm multiplication of omega c, we can write it Vm divided by 1 over omega c, and this become amplitude of current, and this cos omega t can be written as sin omega t plus 90 degree, a sinusoidal wave with 90 degree leading phase position. So our capacitor current become Im sin omega t plus 90, and this trigonometric expression clearly indicate that this Im is peak magnitude or amplitude of current, and current leads voltage in phase by 90 degree. So in pure capacitor, in alternating current supply, both voltage across capacitor and current through capacitor are sinusoidal alternating quantities of same frequency, but the phase of current leads voltage by a phase angle of 90 degree, and positive peak or positive to negative zero crossing, all of current comes 90 degree in phase ahead of voltage in time. And as told earlier, it is quite easy to remember that current leads in capacitor because both current and capacitor got identical spelling start. C, that means in capacitor current leads. When standard reference sinusoidal voltage is applied across capacitor, that will start with 0 instantaneous magnitude at t equal to 0, and at that very instant current starts with positive peak value, and peak of current leads peak of voltage in time or phase by 90 degree, as it is clear from this wave diagram. We can say voltage is a sine wave and current is a cosine wave, and cosine wave leads sine wave in phase by 90 degree or a quarter of a cycle. During positive current condition or in positive half cycle of current, the voltage across capacitor continuously increases as charging current increase charge on capacitor and increase its voltage, and during negative half cycle of current, this discharge current continuously reduce voltage across capacitor, and this is also true as charge is proportional to voltage and current become time rate of charge flow proportional to time rate of voltage change, and positive current means positive change in voltage with respect to time, and as time increases voltage also increases for positive charging current, and for negative charging current dV by dt become negative. That means increase of time will result in decrease of voltage magnitude as shown by this orange characteristic here. The time rate of change in voltage is directly proportional to charging current, and when charging current is at positive peak at that instant, the rate of change of capacitor voltage with time is maximum, and voltage increases at maximum pace when its instantaneous value is 0 as shown here. Similarly, at negative peak current conditions, the negative rate of change of voltage with time is again fastest. Again at 0 instantaneous value conditions, the rate of change of voltage is maximum, and both at positive peak and negative peak, the rate of change of voltage with time become 0, as at those instant the charging or discharging current becomes 0. So when charging current is maximum, voltage is changing at maximum rate and charging increase voltage, and as charging current decreases, rate of change of voltage decreases, and when charging current becomes 0, the increase of voltage ceases, and when charging become discharging, the voltage in place of increasing start decreasing. For smaller discharge current, rate of change of voltage is small, and for high discharge current, rate of change of voltage is high. This graphical presentation of sinusoidal time varying alternating voltage and current in capacitor relationship, where current leads voltage in phase by 90 degrees, also represented by phasor diagram, and in this phasor diagram, the current phasor in anti-clockwise direction by 90 degree represent that current leads voltage by 90 degree in this pure capacitive circuit. Both voltage phasor and current phasor are rotating vector of same angular frequency or same angular velocity, and their projection on vertical axis at any time instant represent their instantaneous magnitude. At t equal to 0, voltage at horizontal reference indicate 0 instantaneous magnitude as its projection on vertical axis, and current represent maximum peak magnitude as its projection on vertical axis at t equal to 0. And after 90 degree rotation in anticlockwise direction, the instantaneous position of phasor represent 0 instantaneous magnitude for charging current and peak voltage across capacitor plates. During this time interval, the projection on vertical axis of current continuously decreases and projection of voltage on vertical axis continuously increases. It represents that charging current is decreasing and charge and voltage across capacitor by charging is increasing. Further rotation of phasor alter the sign of current and current become discharging current, and projection of voltage on vertical axis decrease. That means discharging current reduce voltage and charge on capacitor, and at this time instant discharge current become peak negative and charge on capacitor plate becomes 0. Further rotation reduce discharge current magnitude and increase voltage with opposite polarity on capacitor plate as shown by phasor diagram, and at this instant discharge current becomes 0 and capacitor will have negative peak charge and voltage across it. As time progress and phasor rotates, the current become charging current and negative charge and potential of capacitor reduce and become 0 when charging current become peak. So we got that voltage and charge alteration is sinusoidal alteration and charging current is co-sinusoidal alteration, and in sine and cos, when one got peak magnitude, whether it is positive or negative, the other got 0 instantaneous magnitude and vice versa. In pure capacitance, the peak magnitude or amplitude of charging current got a relation with peak magnitude or amplitude of applied voltage as Im is equal to Vm by 1 over omega c, and if we divide by root 2 both left and right side, Im by root 2 become RMS charging current and Vm by root 2 become RMS voltage across capacitor, and we can say current in capacitor circuit is voltage divided by 1 over omega c, and we call 1 over omega c as Xc or capacitive reactance, where capacitive reactance is 1 over omega c, and this Xc got the same dimension as that of R, ohm, and voltage divided by reactance become current. But in pure resistive circuit, when we apply alternating voltage, the current of resistance remains in phase with voltage across capacitor, whereas in capacitor, the current of capacitor circuit leads voltage across capacitor by 90 degree, and due to that 90 degree phase difference, capacitor store and release energy and won't consume energy as resistance do. So this property of current opposition that demand proportional voltage for current flow is not called as a resistance, but we call it reactance, and we can say capacitive reactance is that property of circuit which oppose alternating current flow across it, and for alternating current flow demand proportional voltage but won't consume electric power. It only store energy when voltage is increasing and release the same amount of energy when voltage is decreasing. So capacitive reactance of capacitor circuit oppose current flow, and for current flow demand proportional voltage. We can say capacitive reactance is a ratio of voltage applied across capacitor to current flowing through capacitor circuit, and it is 1 over omega c or 1 over 2 pi fc. And if we increase supply frequency, capacitive reactance continuously decreases in a hyperbolic manner, with increase of frequency as shown by this black characteristic, and for constant magnitude of applied voltage, variable frequency results in increase of current for increase of frequency in a linear manner as shown here. For DC supply, frequency is 0 and Xc become infinite, and for infinite value of Xc, DC voltage current across capacitor remains 0 after the initial brief duration transient charging current. We know that product of instantaneous voltage across capacitor and instantaneous current through capacitor become instantaneous power of capacitor circuit, and if voltage is Vm sin omega t and current is Im cos omega t, then instantaneous power is Vm Im sin omega t cos omega t, and if we use trigonometric identity of sin 2 omega t, which is 2 sin omega t cos omega t, we can write 1 sin omega t cos omega t as sin 2 omega t by 2, and Vm by root 2 is Vrms and Im by root 2 is Irms. So Vm Im by 2 become Vrms and Irms product, and we got that instantaneous power of capacitor is Vi sin 2 omega t. It's a double frequency sinusoidal variation with peak amplitude, product of RMS voltage and current, and we know for sine and cosine full cycle average is 0. So this power in capacitor for alternating supply got its average value 0, and this is also true because during increase of voltage, capacitor stores voltage in either polarity, and during decrease in voltage magnitude in either polarity, the capacitor release the same stored energy, and for full cycle total stored energy and total released energy is equal and opposite, and average power consumption of capacitor becomes 0. During these two blue framed quarters, the voltage is increasing in either positive polarity direction or in negative polarity direction. The instantaneous power is positive, as at that time when there is a positive direction increase in voltage, the current is positive, and the product of positive voltage and positive current become instantaneous power positive, and when voltage is increasing in negative or opposite polarity direction, the discharge current is also negative, and product of negative instantaneous voltage and negative instantaneous current again become positive. So this capacitor with one polarity is increasing polarization in dielectric substance and storing energy, and at that time source supply positive power to capacitor, and in this quarter source again supply power to capacitor, and capacitor with opposite polarity store energy by increase of polarization in dielectric, whereas in this other two quarter sections, when voltage is decreasing in positive direction, current is discharge current, and when voltage is decreasing in negative polarity, current is charging current, and one out of instantaneous voltage and current is positive, another one is negative, and the product of two is negative power, and during this negative power, capacitor release electrostatic stored energy from its polarized state of dielectric to external circuit, and power flow for that release of stored energy become negative for capacitor as shown here in this yellow highlight. From this power diagram, it is clear that when sinusoidal voltage and sinusoidal current got a 90-degree phase difference, the average power of circuit becomes 0, though the circuit got effective RMS voltage applied across it and effective RMS current flowing through it, but with 90-degree phase difference between current and voltage, the average power in circuit becomes 0, and such power which represent store of energy during positive part and release of stored energy during negative power section is known as reactive power, and circuit element like capacitor which have only reactive power flow is known as reactance. So in pure capacitor circuit, though there exists RMS voltage across capacitor and RMS current through capacitor, but due to 90-degree phase difference between circuit current and voltage, the average power consumption of such circuit is 0, and power in such circuit is only reactive power, and with 90-degree phase difference, the product of RMS voltage and RMS current is known as reactive power. Reactive power is measured in volt ampere reactive, and since capacitor current is voltage divided by capacitive reactance, so we can also write reactive power as V square upon Xc. And in such circuit where current leads voltage by 90 degree, average power or active power is 0 and all power is reactive power, and such circuit property which oppose alternating current flow and demand proportional voltage for current flow is known as reactance. The best part of today's learning class is the explanation of this sinusoidal time varying alteration of voltage and current in pure capacitor circuit when connected to alternating supply, where current leads voltage by 90 degree phase, and in that condition one got peak instantaneous magnitude, the other got zero values, and when out of current and voltage one is increasing in one or another direction, the other one is decreasing, and we can explain this behavior in 4 quarter cycles. Let's take this A to B cycle when charging current increase voltage and charge across capacitor, and when charging current got higher magnitude, rate of change of voltage is higher, and when charging current got reduction in magnitude, the rate of increase of voltage keep on decreasing. Initially at time position A, capacitor won't have any charge, but circuit got maximum charging current, and due to that charging current, plates will have increase of charge and voltage across, and in the process charge and voltage across capacitor goes on increasing. For higher amount of charging current, rate of change of voltage with respect to time is higher, and as charging current becomes 0, the rate of change of voltage becomes 0 and increase of voltage cease, and voltage attain its peak magnitude at time instant B. And in this first quarter cycle, capacitor from 0 charge condition get fully charged. In the next quarter, at the beginning, capacitor is fully charged and there is no charging current, but just after that capacitor start discharging and discharge current direction get changed, and by that discharge current the charge and voltage across capacitor decreases, and when decreases at slower rate the discharge current got smaller magnitude, and when voltage decrease at a faster rate the discharge current attain peak magnitude, and at position C capacitor get fully discharged and circuit got maximum value of discharge current. In this C to D quarter cycle, in the beginning capacitor is fully discharged and circuit got maximum magnitude of discharge current, and same discharge current will reverse polarity of charge on capacitor plate, and capacitor get charged with opposite polarity and voltage will increase with reverse polarity on capacitor, and when discharge current got higher magnitude, this reverse polarity charging is at higher rate, and when this negative current becomes 0, the rate of increase of voltage in opposite direction cease and capacitor will get fully charged in opposite polarity and the current becomes 0, and the same cycle of charging and discharging will take place onwards. RMS value of current in capacitor circuit is given as RMS voltage across capacitor divided by capacitive reactance, and capacitive reactance is 1 over omega C. So we can say current in capacitor is omega C multiplied by capacitor voltage, and if omega is 2 pi f, then capacitor current is directly proportional to supply frequency or capacitance value for fixed value of applied voltage, and if we increase capacitance value in circuit, higher capacitance means higher amount of charge for same voltage, and as voltage changes, higher amount of time rate of change of charge will take place, and higher amount of dq by dt means higher amount of current in circuit. So as we increase capacitance value for fixed supply voltage magnitude, capacitive reactance decrease in hyperbolic manner and current increases in a linear manner. Similarly, if we increase frequency of supply, higher frequency means faster variation of sinusoidal alternating current with smaller time period, or higher time rate of change of charge, and higher dq by dt means higher amount of current. So as supply frequency increases, Xc capacitive reactance decreases and circuit current increases. By this great learning video, we have explained each and every aspect of pure capacitor behavior in alternating current supply. We have explained how in capacitor current leads voltage by 90 degree, and in those conditions average power of capacitor circuit becomes zero and power is only reactive power, which results in store of energy when voltage is increasing and release of the same energy when voltage is decreasing. We have also explained the variation of voltage and current for the entire cycle of capacitor with great detail, so that you can understand this concept with great clarity and ease. Our other learning video of the same playlist are equally useful, and you can use them in your studies or refer them to your friends. And if you need exam centric notes or online doubt clearing classes from this YouTube channel, do join our membership. Thank you very much. Happy learning. Have a nice time.